are really good things to do to practice. It's just more practice because you know how we talked about repetition, repetition, repetition for this chemistry course? Fires those neurons, grows those dendrites. Okay, so that would be a really good tool for you to use. But now these are all going to be pieces of the pie, right? So you're going to have practice problem sets, lecture, PowerPoints, things we do in class. And then you got the homework and the learning objectives. So those are all together. They make all the pieces of a pie. So if you want a really good grade, you need to do all of them. If you focus on just a few of them, then your grade will diminish accordingly. Okay, so the more you use of all those pieces, the better off we'll be. So think about that. There's lots of tools and resources, but you do have to take advantage of those to be able to be successful. And if we're struggling with purchasing a textbook, we do have books on reserve in the library and also in the Science Tutor Center. So if you have an old edition and you're just like, hey, what's the new one saying about this, then you can always go there and read them. Or if you can't get your book right now, you can, at least it's on reserve so that you can have access to that. Okay, so I just wanted to let you know about that as well. Okay, well, we left off talking about sig figs. Yay, did we practice with those sig figs? Okay, because that was Tuesday, this is Thursday, so we were all supposed to study within how much time when we leave lecture?
24 hours.
24 hours, or else it starts to fade. So I hope we studied it and nailed that down. Now, do you remember leading zeros? What did we say about leading zeros? Never significant. Middle zeros? Always end zeros? Only if there's a decimal. Okay, and do you remember when we talked about calculating with those? Yeah, so when you're adding and subtracting, answer needs to be in least number of decimals. Very good. Multiplying, dividing, least number of sig figs. Okay, don't mix up those. The sig figs the exact same thing as the decimal? No, so don't mix those up. Now, when you're measuring things, remember we talked about that? You measure something, and you're going to take all the markings, and then what? An estimated digit that occurs between the marks, right? Okay, so you need an estimated digit. So it's always one estimated digit whenever you're measuring anything. So we'll do that in lab. Okay, and then we practice doing a calculation, because how many times can you round? Once. And when do you round once? At the end. Okay, yay, awesome. You guys have got that down. So we did a practice example, didn't we? Okay, so remember how we did that? All right, well, let's just put up another one just to kind of refresh our memory. And then I want you to do one. All right, so let's do this one. 8.02 times 3.1 minus 14.84, parentheses there, times 0.55. Okay, and do what's in parentheses first, so it's multiplication and division. So the rule is least number of sig figs. Okay, so how many sig figs here? 3. How many sig figs here? 2. So what should my answer have? 2. All right, so when I put this in the calculator, am I going to round here? No. So what am I going to do to indicate 2 sig figs to remind me? I'm going to box it. So I'm going to box off 2, right? But when you type this in your calculator, you're keeping all the numbers, aren't you? Okay, don't round here, but we have to keep track. So this is just a mental way to keep track, unless you want to just memorize that it's 2 and remember. You can do it that way too, but I think it's easier if we just box it off. Then you don't have to try to remember. All right, so then the same thing here, minus, and the same thing. So I've got how many sig figs here? 4. How many sig figs here? 2. Okay, so my answer has to have how many? 2. Okay, so here's the answer in the calculator. So I'm going to box off 2. Don't round. You're not going to say 8.2. You're going to leave it at 8.162. Box off the 8.1. Here's 24.862. Box off the 24. Now I'm subtracting. So what's the rule when I'm subtracting? Least number of decimals. Okay, now, remember we're trying to keep track. So you count what's in the box. Okay, count what's in the box. How many decimals are in this box? 0. How many decimals are in this box? 1. So my answer should have how many decimals? Least number. 0. Okay, does everybody see that? You count what's in the box. So it's going to be 0 because that has 0 decimals, that has 1, and the least number is 0. So I'm going to count what's in the box. So my answer has to have 0. So when you put that in your calculator, you get 16.7. Okay, but I have to have 0 decimals, right? So that would round to exactly 17. All right, does that make sense? Okay, awesome. Now I want you to do one. Okay, so we're going to do this one. This is 24.6681 times 2.38, and that's in parentheses, plus 332.58. Okay, I want you to do that one. Okay, so see if you can work on that one and see if you can figure out what that should be. Paying attention to our sig fig rules. Oh, sorry, Anna. Great, thank you. Okay, so everybody sign the roll. You missing anyone? Okay, I was about to say, I think I'm missing a couple people. Okay, so everybody else sign the roll? All right, awesome. Okay, looks like we're getting it. Yeah, we're doing over here. We're doing okay? It's okay, sorry. Okay, how are you guys doing over on here? Good? Doing okay? Tam got it? Everybody? Okay, so it looks like we got it. Okay, great. Now check with your neighbor. Make sure you have the same answer, and if you don't understand it, explain to each other why or why not. So get together, talk about it, and if the people next to you have the same answer, check the other direction. Turn around and check with somebody. Okay, so turn to your neighbor sideways or behind you. Check your answer. And if you don't remember their names, introduce yourselves. Okay, so make sure you know each other's names. If you see, remember them from Tuesday.
That's why you're getting it.
Okay, did you guys check? Yeah? Okay, how about you guys? Did you guys check? All the same? All right. Okay, did everybody understand it? Check to make sure everybody around you understands it. Do you have the same answer as the people around you? Is it Casey?
Yep.
Casey, do you have the same answer? Okay, tell Casey your name. This is Casey, and you were? Alina. Okay, Casey and Alina. Oh, yeah, then you missed the other. I was like, I don't remember your name. Okay. Yeah, so check your answers. They should be exactly the same. And if they're not, why not?
Super interesting.
I try to do the practice, the one practice, and if you have, let's say this one is 7, this 0 is 7, and this one remains 9.
You have to go up one. Okay, so to
Do
go
you
up.
start approximately from 7 to 9, then going to 2?
Yes, because think of it as 29. If you're going to go up one, what does 29 become?
30.
30. So then that becomes 30, not 29.
Okay.
Right?
Yes. Okay.
Yeah. Okay. Or if you're not sure, find your lab partner and ask them questions. What did you guys get for your answer? 391.3. Oh, okay. Do you have it? No, yes. If you don't, find out why not. Okay, so turn around and find somebody who's got the 391.3 and ask them, why is it not that? Okay, so double check. All right, ask somebody why you don't have that number if you don't have that number. Does everybody have it? Does everybody understand why? All right, what are we thinking? Questions? Okay, you remember to box off your answer after the first step, right? Okay. All right, anybody have any questions or anything about that one? We're good? Awesome. Okay, yay, we got that. All right, that's so easy. We've done it with one step. Now we've done it with multiple steps. Oh, this is so easy. Well, let's bring in more. Okay? Yay, let's do one with exponential notation. That'll be fun. Yeah. All right, let's do that one. Okay, let's do this one. Let me show you how this works. 85.3 minus 21.489 divided by 0.059. Okay, so we're going to do what's in parentheses first, and you know that's subtraction, so it's least number of decimals. Okay, so let's do that one. So 63.811 divided by, and then I'll rewrite that, 0.059. Okay, least number of decimals. Well, how many decimals does this one have? 1, and the other number has 3, so the least number is 1, so I better box off 1, right? So it's going to be 63, what? 0.8, very good. Now divided by 0.59, so it's least number of, we're dividing sig figs. All right, now, when you count the sig figs, which ones are you going to count in this first number? All the sig figs or in the box? But you're going to use all the numbers in your calculator, but you're going to count the ones in the box. Okay, that's why we put the box there, to help us keep track of that. So we're going to count the ones in the box. So how many sig figs are in the box? 3. How many sig figs here? 2. So my answer should have 2 sig figs. Okay, so when I put this, I get 1081.5422373. And I'm only supposed to have how many sig figs? 2. Wow. How am I going to write this showing only 2 sig figs? All right, this is where we use scientific notation, right? Okay, so I got to have this. So can I write down 11?
No.
No, because 1,081 is not the same thing as 11. If somebody owes you $1,081, you're not going to accept 11, are you? No. So we would write that 1.0815423. Let's go ahead and put it in exponential notation times 10 to the what? 3. Okay, now I want to box off my 2 sig figs, so this rounds to 1.1 times 10 to the third. And that's how you would put it in. Now there's another way you could have done it. You could have said 1100. Now there's no decimal here, is there? So if there's no decimal, those zeros don't count, and so how many sig figs does this have? 2. So this is the other way you could have done it. You could have written it as 1100 with no decimals. That marks 2 sig figs, or you could have written it like this. Usually this one, but it's totally acceptable to do this one with the 00. It's totally fine. Exponential notation is what we a little bit prefer, but totally fine the other way. Okay, that makes sense? Okay, great. Oh, this is so easy. Well, great. Now that you can do that, let's just add one other eensy-beensy rule. Okay? One more eensy-beensy rule. Now, when you are working with scientific notation, if you are multiplying and dividing, so this is scientific notation. If you are multiplying and dividing, the rule is the same. That's fine. It's the way it's always been. Okay, you just count the sig figs as usual. But if you are adding and subtracting, then there's another layer that we have to add. And that is that if you are adding and subtracting, your exponents, the exponents must be the same. That's like saying apples and apples. You can't compare apples and bananas. They're not the same thing. They're fruit, yeah, that's true, but they're not the same. So what we want is to be exactly the same in order to count the decimals. With sig figs, it doesn't matter. It's only the adding and subtracting that it does. Okay, so this is our one other additional little rule. No problem, right? So let's do an example of that. 282.4 times 10 to the 5th minus 1.100 times 10 to the 3rd times 2.8973. Okay, so these two numbers are going to be in parentheses. So we're going to subtract these and multiply it by the 2.8973. All right, so let's do what's in parentheses first. Now, we've got exponential scientific notation, don't we? So what do we say? What has to be the same? The exponents. All right, let's take a look at the exponents. I have a 5 and I have a 3. Are those the same? No. Oh, we got to make them be the same. Okay, now the question is how are we going to make them be the same? We're going to move the decimal on one of them. Okay, and I would move the decimal on this one. Okay, it's a 3. I got to move it over, until we get to 5. So I'm going to do that. So I'm going to move it over 1, 2. So this would be 282.4 times 10 to the 5th minus 0.01100 times 10 to the 5th. Now they're the same. Okay. Now the reason why I would want to move this one is because zeros in the front, does that ever affect the sig figs? No. So this is a good way to go. Zeros in the front. Doesn't mess with any sig figs. I'm fine. Now if we had trouble trying to go from here to there, we're like, oh wow, I don't know if I can do that. Then let's just break it down. 1.100 times 10 to the 3rd. Go ahead and expand this out. This is a positive number, so does that mean it's going to be big, right? Okay, so 1, 2, 3. So this becomes 1100. Now, if you want to be 5, then don't I need to move this decimal back 5? 1, 2, 3, 4, 5. So this becomes 0.11100 times 10 to the 5th. Okay, so you can step it out like this. If you have trouble thinking, all right, I got to move it 2 to the left. Maybe you might get confused and move it 2 to the right. Okay, so break it down. Remember, if it's positive, you want to go to the right, make it be a big number, and then whenever we're talking about scientific notation, you move that many decimal places to the left, but you leave it positive because when you expand it back out, it's going to be a big number. So positive, you expand it back out, it's a big number. All right, so this is how we would do it. Now it's the same. So yes, you can go ahead and put that in your calculator, but your calculator will give it to you with an exponent that's not 5. You still have to keep it the same in order to compare apples to apples. So I still have to keep it to the 5 exponent. So it would be 282.389 times 10 to the 5th. Now in your calculator, it'll give it to you times 10 to the 7th. You can't count decimals if it's 10 to the 7th. Why not? Because what did we say? The exponents, what? Must be the same. So when your calculator gives this to you as a 7, is that the same? No, we got to make it be 5 again. It has to be the same. To subtract them, they have to be the same. To count them, they have to be the same. So they all got to be 5. Now, let's count the decimals. How many decimals do I have here? 1. How many decimals do I have here? 5. Do you see that? 1, 2, 3, 4, 5. 5 decimals in this number. And over here on this number is 1. So my answer better have how many? 1. I can count it because it's the same exponent. So here's the 1. 282.3. That's what I'm boxing off. Does that make sense? Has to be the same exponent, and then I can count decimals. Now, you don't need to do that with sig figs and multiplying and dividing, just only when we're adding and subtracting. Okay, so they're same exponent, count out the decimals. Now I keep going. Now, since I'm multiplying and dividing, what does my answer has to be in least number of what? Sig figs. Do I care about exponents now? No, I don't care. Let's just count sig figs. Remember to count them where? In the box. How many sig figs are in the box? 4. How many sig figs over here? 5. Okay, so my answer better have least number, which is 4. Now, in this case, it's totally fine to change the exponent because, hey, we don't care. It's multiplying and dividing. And remember how we talked about scientific notation? You just want one digit and then the decimal. All right, so this would be 8.1. This is how your calculator gives it to you. 8.181656 times 10 to the 7th. That's fine. You can have a 7 exponent. That's fine. That's the way your calculator does it for you. Great. It doesn't have to be 5. In fact, we want it to be 7 because then there's only one digit right here. Okay, and then we box off, we said 4 sig figs, right? No, what did we say? Yeah, 4 sig figs. 1, 2, 3, 4. Okay, so this would be 8.181, but then we round it to 8.182 times 10 to the 7th. And that's your final answer that you would put in. Okay? Make sense? Yay, we got it. So got it. All right. Excellent. So that's the one other additional thing that we need to do in our calculations with sig figs calculations in multiple steps. All right. Yay, we got that. Okay. Whew. Well, that's the digit part. Oh, by the way, you guys know how to type this into your calculator, right? You know how to put that in? Okay. How are we putting that into our calculator? How would you type in something like 1.3 times 10 to the 2? How would you type that in your calculator? How would you do it? 1.3 times 10 caret 2. Okay, that's not a very good way to do it. I know that's a common way to do it. We all do it that way, but I wouldn't recommend it. Yes, because the problem with this is that the calculator will do order of operations. So it will multiply these two and raise the whole thing to the power of 2 and square it, unless you put this in parentheses. So you either put that in parentheses all the time, which is a lot of numbers that you're putting into the calculator, or we have what's called the EE button. So if you're looking on your calculator, can you see that EE button? Okay, so what you would do is 1.3, and then you would hit that EE button, and then say 2. No times, no 10, no caret. Do not put times 10, because then that increases all your answers by a factor. So don't do that. This EE does mean times 10 raised 2. So you would say 1.3 EE button, and then all you do is 2. Does everybody see that on your calculator? Did everybody find your EE button? It may be a different color. If it's a different color, you might have to push that second function, different color, on your calculator. Okay, so everybody can find it? It might be green. Your EE button might be green, so you're going to have to push the green button first. Might be green letters above another button.
So we couldn't use this exponent too right here? For the exponent? We can't.
Nope, that means squared. It means you're squaring the whole number. Don't do that.
Okay.
Do not do that.
Okay.
Do not do that. There you go. And then 2. No times. You don't put a times. Do not put times. Do not put times. This is all you're putting. 1.3 EE button, 2. No times, no 10, no caret. Nothing like that. Okay, does everybody see that? 1.3, and then hit the EE button and 2. Now when you do that, your calculator's going to know, hey, I know what you mean now. And then you don't have to keep putting that in parentheses all the time. Exactly.
When I put this exponent 2, it still was 1/3.
Yeah, but don't do that, because what if it's not a 2? What if it's a 3? And then you have to say times 10. So now you're starting that whole thing. And then if you do that, then you're going to have to put parentheses around the whole thing again. You have to have parentheses if you do it that way. So look what all you're putting in, which is more room for error. What if you forget the parentheses? You're done. The calculator will give you an incorrect answer. If you put this in parentheses, you can use this, but it's going to take a lot more time and effort, and there's more room for error. I would do it this way. Okay, so I suggest you do it this way all the time. Now, some of us may not have an EE button. You may have what's called an EXP button. Okay, does everybody have an EXP? Some of these calculators have EE buttons. These kind usually have an EE button. Okay, this kind of calculator over here has usually maybe an EXP button. Oh, you have an EE? Okay, some of them that look like this have what's called an EXP button. Does the same thing. Okay, so you either use EE or you use EXP. All right, so might be an EXP button. There you go. There's an EXP button. Okay, so you would use that one and not an EE. Your calculator? No, she does not have an EE on this one. Instead, she's got EXP. Okay, it means the same thing. You do it the same way, except you're using EXP. All right. Yeah, and she doesn't have to do the shift thing. She just got that going on. That was like easy. All right, awesome. Okay, those are numbers. What we want to talk about next is now when we're talking about measurements, didn't we say, hey, there's a number and what else do we put with it? A number and we need like 24 units. Okay, so we got to have a unit. So let's talk about the units. Now we have different unit systems. We have the English system. Okay, you guys know the English system, yards and all of that stuff. If you're not familiar with the English system, like how many feet in a yard or how many quarts in a gallon, those kinds of information pieces will be put in the exam or it's on the back of the periodic table. But the metric system, you're going to need to know that. We will not give those to you. Okay. Now there's also the SI, System International. What does that mean? Well, that means that, look at all these things. Look at all these distances, which one is the standard one? That's what the SI unit is. Okay, well, let's talk about this metric system. Are you guys familiar with the metric system? Yeah. Okay, you know how it works by powers of 10?
Yeah.
All right. All I'm going to say then is memorize these. Okay? There are more, but we don't need more. This is fine. You know, back in the day, giga and mega and all those used to be unknown, but now, gosh, with computers, we're like, oh yeah, how many gigs is that? You know, we use that in everyday vernacular. So, memorize this. I do want to draw your attention to the way that these are written. Be very careful. I like to memorize it this way. So I put this in here, and this is the way I will do it in class because it's easier for me to remember. Like if I say centimeter, century, what are we thinking? 100. So it's easy for me to remember centimeter. 1 meter is 100 centimeters. So that's the way I memorize that. Okay, so let's talk about that. One meter is 100 centimeters. That's the way I like to remember that. Or in other words, to write 100 centimeters, I could write 1.0 times 10 to the 2. I can do that, right? Okay, but look at the other way. Now we're saying instead of 1 meter, I'm talking about 1 piece of a meter, which is called a centimeter. So 1 centimeter is how much of a meter? 1/100th, isn't it? Okay, so 100th, which is another way of saying 0.001, which is another saying 1.0 times 10 to the minus 2 meters. Now this is where it can get really confusing. A minus 2, positive 2, look how similar those numbers are. This is in centimeters, this is in meters. Sometimes we reverse that a lot. So be very careful on which way you've memorized it. I like to do this one, and I'll do this one in class. If you've memorized it this one, then just go with this one. Don't mix and match. Do one or the other. Don't mix and match. It makes it harder. Okay, so that's the metric system. Now we talked about these prefixes. So meter is the base unit, and then you've got gigameter, decentimeter, millimeter. But you can also do the same with liters, right? Milliliter, centiliter. You can do this with grams. Milligram, centigram. You can change those units. Gram means what? Mass. Liter is volume. Meter, length. Okay. Now you know a meter squared is now an area. Okay, how about a meter cubed? It's volume. Okay, that's a meter is about like this. Okay, this is a meter cubed. Now the SI unit is the standard. So length is meter. You would think volume would be liter, right? But it's not. You're like, why is it not? You know, why can't we do that? Okay, it's not. You would think it would be, but it's not. Okay, well, let's think about what a meter is. And for volume, it's the cubic meter. Okay, it's meter cubed. That's the standard for volume. And you're thinking, well, how much is a cubic meter? Is that a liter? No. This is a liter. A liter is like this. A cubic meter is like this. Okay, so that is not the same. In case you don't know how much a liter is, it's almost like a quart. I'll pass that around. You can take a look at that. So 1 cubic meter is not a liter. Well, what equals that liter? 1 cubic decimeter. Okay, that's a liter. So don't be thinking a cubic meter is a liter. It's not. It's a cubic decimeter. And another thing you might want to keep in mind, this is 1 liter. Another unit we use a lot is 1 cubic centimeter. For those in nursing, 1 cubic centimeter equals what? 1 milliliter. Okay, we're going to use this one a lot, so you might want to keep that in mind. What's another word for cubic centimeter? Those in nursing? cc. So nursing says 1 cc equals 1 milliliter because cc stands for cubic centimeter. Okay, so you might want to remember that. All right, that's the metric system. You do need to know the metric system. Okay. Now, let's talk about the things that we measure. Now, remember, we take all the marks plus 1 measured estimated digit. So let's talk about the things that we're going to measure. And one of the things we measure is temperature. So you know what happens to the molecules if we increase the temperature and we add heat and temperature is increasing? What's happening to the motion of the particles? They get faster, right? So the more you heat it up, the faster we go, right? You're just like, faster, 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 I'm heating it up. Whoa! Okay, that's the way the motion goes. Now let's talk about the 3 scales. You guys are familiar with these 3? Yeah, we use Fahrenheit all the time. Water freezes at 32, boils at 212. This is Celsius. It's kind of like the metric one. Water freezes at what? 0 and boils at 100. Nice even numbers. Just 32 and 212. You're just like, All right, so this is a reference point. Now, 100, 0 to 100 means 100 marks. 32 to 212 is 180 marks. So is 1 degree Celsius the same as 1 degree Fahrenheit? No, it's not. Because I got the same amount is divided into 100 intervals. This is divided into 180. So 1 degree is not the same, right? And of course we know the temperature reference is different. Well, we said the more you heat up an object, the faster the motion goes. Okay, well what happens if you start cooling it down? What happens? Slow it down. Gets cooler. And is there a point where you're just thinking, okay, what's as cold as I could get? Wouldn't that mean I'm slowing it down until all motion stops? I mean, you can't get any colder than that, right? Okay, all motion stopped. And what would that be? Absolutely as cold as we could go, wouldn't it? So we're going to say absolute 0. And that's our other scale. That's the Kelvin scale. So the Kelvin scale, absolute 0 is as cold as we can go. Well, if 0 is cold as we can go, then what does water freeze at? Freezes at 273. Now, to be more accurate, it would be 273.15. Okay, but for this course, we're going to just stick with the 273. Are we okay with that? All right. Well, it's not as accurate, but we're just going to go with that for this level. 273 is where water freezes. So water boils at 373. So there are how many marks between 273 and 373? 100. Okay, so does that mean 1 degree Kelvin is equal to 1 degree Celsius? Yes, it does. And we'll use that later. But 1 degree Celsius is the same as 1 degree Kelvin. But the temperature reference points, are those the same? No, so be careful. Now, if you want to convert between 0 Kelvin and our Celsius and Kelvin, what do we have to do to convert between Kelvin and Celsius? Add 273 to which one? Celsius. All right, so that's one of our equations. That would be Celsius plus 273 equals Kelvin. Okay, and you guys can do that one, right? We're comfortable with that? Okay, that formula is provided on the back of the periodic table for you, temperature formulas. Okay, and then let's talk about the other ones. How about going from Fahrenheit to Fahrenheit to Celsius? Fahrenheit to Celsius. All right, here's our equations. Now let's think about where it came from. 32. Why are we talking about 32? Well, what temperature does water freeze on Celsius? 0. What's the temperature does it freeze at Fahrenheit? 32. Okay, there's the difference right there. So we got to take into account 32. What about this 9/5 thing? 9/5. Well, there were 180 marks, and there were 100 marks. So what's the ratio of 180 to 100? 9/5. Or you might see it as 1.8. Sometimes you might see the formula be 1.8 right here. Well, that's 180 to 100. So that's where the formulas came from. Again, this is going to be on the back of the periodic table. So are we comfortable with doing temperature conversions? Yeah, all right. So you do need to be able to do temperature conversions. Okay, well, there's another thing that we measure. And let's see if you can tell me about this one. Oh, as far as weights go, if you may be familiar with kilograms, okay, we passed around a liter. I was just curious to see how much a kilogram weighs. So this is 1 kilogram. So if you want to feel the weight of 1 kilogram, yep, exactly, 2.2 pounds. That's how much that would be. So let's talk about another thing that we can measure. All right, so let's see if we can do this one. Okay. This is baking soda. Now you know this is vinegar. With what happens when we put vinegar and baking soda together? Do we get a reaction? Okay, how do you know that? What's going to happen? Fizzing, right? So fizzing occurs. Okay, so if I put this, now because you see fizzing, that means a gas is being released, right? Okay, so that means you know reaction's happening, isn't it? Okay, we talked about chemical properties. So when you put baking soda and vinegar together, the chemical property of baking soda is that it releases a gas. If I put gold and vinegar together, am I going to get the same thing? No. No, we wouldn't. All right, so, and if you guys know, do you guys know what's being released? Carbon dioxide. So this is the kind of same thing that happens when you put seashells in vinegar, and we talked a little bit about that. All right, so, whoop. All right, so that's producing CO2. All right, so let's light this candle. All right, now I want you to watch the flame. Okay, so watch the flame, and I'm going to pour this on top of the flame. Okay, so let's see what happens. Okay, I'm going to pour all this on top of the flame. All right, so here we go. Give it a second to do its reacting. All right, here we go. Oh! What happened? It went out? I didn't even get to pour all that on there. Why would it go out? What it needs oxygen. Doesn't a flame need oxygen? Okay, so if there's no oxygen, that means I've smothered the flame somehow. How would I smother the flame? With CO2? You mean I can pour CO2 through the air and it lands on the candle? What? I can pour gas through another gas? Yes, you can. CO2 is heavier, or we should say not heavier, but denser. So by going like this, you can't see CO2, but it's in there. And so by tilting the beaker, what happened is the CO2 poured out, landed on the candle, and smothered it. So we call that not so much heavier, but we call that density. So that's another thing that we're going to measure is density. There's an old riddle that says, which weighs more, a ton of bricks or a ton of cotton? They're both a ton, so the answer would be the same. A ton of bricks weighs the same as a ton of cotton. They're both a ton. But if you were thinking bricks, what you're not thinking about is how much it weighs, but you're thinking about its density. Yes, bricks would be more dense. So what is density? How do we define density? Density is mass over volume. Very good. Okay, so density is defined as mass over volume. Now we need to remember it's mass over volume, not volume over mass. Okay, we always get that mixed up, especially on the exam, we start mixing this up. Okay, so let's think of a way to remember that. Density is, and I'm going to draw a heart, because don't we love chemistry? Yes, we love chemistry, of course we do. So draw a heart, because we love chemistry. And then I'm going to draw a line through there, and what do we have? M over V. Yeah? Yeah? Okay, so this is what density is. Now, we need to figure out, if I gave you mass and I gave you volume, you can calculate density, right? You just divide those out. But what if I gave you density and volume? Okay, can you solve for mass? Yeah, and since this is divided by, what are you going to do to get volume out of the bottom? Multiply it on the other side, right? So it's volume times density is equal to mass. All right, now what if you're solving for volume? Okay, now do we have trouble figuring out how to arrange that? Because we're like, you said it was mass divided by density. Well, you know, if we have trouble, let's step it out. First we say volume times density is mass. And if I'm trying to solve for volume, then it is mass divided by density. Now, if you have trouble with that, let's do a little cheat sheet triangle. Okay? You've seen this before? Okay, I'm going to draw a line like this. So I draw a line across and one down. So I'm going to put density here. Density is equal to mass. I'm going to put mass over volume. Now, if I want density, I say mass divided by volume. If I want mass, these are side by side now. So it's density times volume. And if I want volume, guess what's on top? Mass. So you must put mass divided by density, not the other way around. Okay, that's another common mistake that we make. Now, how do we measure volume sometimes, especially out of an irregular object? You're going to do this in lab. So if I have a graduated cylinder, and I have this much volume in here, if I drop a block in here, what's going to happen to the volume of water? It's going to go up. How much does it go up by? By the volume of the block, right? Here's the block. So this volume is equal to the volume of the block. So if you're trying to figure out density, can't you just subtract those two volumes and get the volume of the block? And then you weigh the block and you can get density. Great. By the same token, if you have density and mass, if you got density and you have mass, could you predict the volume? Calculate the volume? All right, so if I know the volume of the block, and this is the amount of my solution, could I predict what the new volume should be? Yes. And how would you do that? You would, what? Measuring the mass and the density, and you would, given the density and measuring the mass, you would calculate the volume. And then you could predict, hey, the volume's got to go up this much, because that's the volume of the block. Does that make sense? Now, when we're doing this, density, you have to have it all be the same. Density of the block, volume of the block, not the water. It all has to be about the block. Mass of the block, volume of the block, density of the block. It's all got to be about the block. If I had density of water, it's got to be all about the water. Mass of the water, volume of the water, density of the water. You can't mix and match units with that. Okay, great. Well, here's some different densities. The units of density are grams per milliliter. If you're talking, or cubic centimeter, if we're talking about solids. Grams per milliliter if we're talking about liquids. Those are the densities. Now, if we're talking about gas, it's a little different. It's grams per liter. And when we get into the gas law chapters, we're going to use that as grams per liter. But the units are going to be a little different, so we'll need to remember that, but we'll do that later. Okay, so let's look at CO2. Can you find CO2? Yeah, what's the density? 1.96. How about air? 1.29, which is more dense. Carbon dioxide. So if an object is more dense, it's going to sink to the bottom. That's why CO2 falls through the air. It's going to sink to the bottom. What happens if you put ice cubes in water? Do the ice cubes sink or float? If you put ice cubes in water, what do they tend to do? Float, right? Don't they float at the top? Yeah. Okay, well, let's look at the density. What's the density of ice? 0.92. What's the density of water? 1. So which is heavier? Or more, I should say, more dense. Water is more dense, so it's going to be at the bottom, right? And that's why ice cubes float. Now, that's unusual, because normally solids are more dense than liquids, but water is an unusual substance that way. The solid is less dense than the liquid. That's rare. Okay, usually the solid is more dense than the liquid. Okay, well, let's talk about ice cubes and ethyl alcohol. You guys know ethyl alcohol is the stuff in beer and wine and all that kind of stuff, right? Yeah? Oh, you do now. Okay, so if you had ethyl alcohol, pure ethyl alcohol, and I put ice in it, what's going to happen? The ice would sink, wouldn't it? Yeah, it's more dense than ethyl alcohol. So if I had ice in water, it would float. If I put ice in ethyl alcohol, it would sink. Yeah, exactly. Okay, so that's something that we use with density, and those are some of the calculations that we have. Here's 2 cans of Coke, and exact same volume. One sinks, and the other floats. What's that mean? Okay, oh, that's a good thought. Well, what if they're the same liquid? Now what? They're both in water. One is frozen, one is not. Well, that's interesting, because ice, when it freezes, it expands. So it would be expanding. So we can't expand it. It's the same temperature. They're at the same temperature, and they're in the same water. What's the difference? Is one diet? One is diet. What does that tell you about the densities, though? What does that tell you if this Pepsi is sinking in a beaker of water? What is that telling you? It is more dense, right? More dense. How about this one? Less dense. Okay, well, density is mass over volume. So if the volume is the same and the densities are different, then what has to be different? The mass, exactly, yeah. So actually this is more dense than that one. They would weigh different amounts, and we're thinking, wow, why is that? Well, the difference is actually this is diet. Okay, so the sugar that's present increases the density. When you take out the sugar, it's less dense. So when they're talking about, oh, it's light Coke, they're not kidding. It is lighter. It's lighter mass. So that's an interesting example of density. All right. Well, we measured temperature, we measured density, and we've got all these measurements, and we know how to do sig-fig calculations. Well, let's put that together. What if I want to change one unit from another? Okay, what if I want to change grams and kilograms? Okay, what if I want to change liters to centiliters? What if I want to do that? What if I want to change the units? Because we have to have the same units if we're going to add things together, right? We know that, apples to apples. So I got to convert. Now, you guys familiar with conversions? Yeah, yay, we are familiar. Awesome. Okay, because, we can use this conversion method, dimensional analysis. You might have heard that term that way. The Science Tutor Center will do some dimensional analysis clinics to help you with this. But this is a method we have to get down. We're going to use this all the way through, constantly. So we really, really, really need to nail down dimensional analysis so we can do stoichiometry and other additional things that we're going to do with it. So this is one of our building blocks. So it's very important that you nail this down. So a lot of us are familiar with it. We use it. What's the purpose? The purpose is to convert one unit to a different unit. And that works great in chemistry. You might have done that in physics. If you're cooking in the kitchen, you can use dimensional analysis. I do that all the time when I'm doubling or tripling a recipe and I'm going from teaspoons to tablespoons or, cups. And I bring out the dimensional analysis, and my daughter's like, "Oh, Mother." But it works great. It works great. You know how sometimes when you're converting meters to kilometers, you sort of move the decimal the wrong way? It happens a lot, right? Well, if you use this method, you won't have that problem anymore. You'll always get it right. So that's the neat thing about this. It's got built-in checks for you. So let's talk about this dimensional analysis. Well, what is dimensional analysis? It's the ability to convert between one unit and another. And what are we going to use? We're going to use what's called a conversion factor. So you have one unit and you have the other. How are we going to relate the two together? Conversion factor. All right, so let's talk about what's a conversion factor. You have to be able to generate these necessary conversion factors. Well, what is it? It's a ratio. It's a ratio of one number and unit to another number and unit. Now, conversion factors has to have the number. And can we forget the units? No, we have to have numbers and units. Numbers and units. Now, these conversion factors, okay, we said they're a ratio. You have to have numbers and units. Where does it come from? It comes from true relationships. A true and valid relationship. What's a true and valid relationship? It's when you equate things together, they equal each other, and they have different units. For example, 1 foot equals how many inches? 12 inches, right? We know that. These are different units, but we know this to be this equal. That's a true and valid relationship. 1 foot equals 12 inches. Give me some more. 1 inch is 2.54 centimeters. Give me another one. Okay, 1 milliliter equals 1 cubic centimeter. Very good. How many days in a week? 7 days is 1 week. Okay, so you see how we're getting these true and valid relationships? It's things you know to be equal, and they have different units. These are true and valid relationships. This is what we use to make a conversion factor. Okay, so now we have these relationships. How are we going to get the conversion factor? It's a ratio. Let's take foot and inches. A ratio would be 1 foot divided by 12 inches. But you know what? I could do it the other way too, couldn't I? 12 inches divided by 1 foot. So for every true and valid relationship, how many conversion factors do you get? 2, always 2. Why? You're like, why do we need 2? Well, one of them converts feet to inches, and the other one does inches to feet. So you always need 2. All right, well, let's write some more conversion factors. How would you write a conversion factor for inches and centimeters? 1 inch. Okay, 2.54 centimeters. Or, all right, do you see how we got that? Let's do weeks and days. What would it be? Let's see, let's do days in a week. How would that conversion factor be? 7 days divided by 1 week, or 1 week divided by 7 days. Awesome. All right, so now you know how to get conversion factors. What are we going to do with them? Now that we have them, what do we do with them? We multiply with conversion factors. You multiply and divide. So now you can multiply and divide numbers. We know how to multiply and divide numbers. But can we really multiply and divide units? Yes. What's a centimeter times a centimeter? Centimeter squared. What's a centimeter times a centimeter times a centimeter? Centimeters cubed. What's a centimeter divided by a centimeter? No unit. It's just number 1. It's no unit. They cancel. In other words, we say these cancel. So when you divide the words, you cancel the units. Okay, so dividing words, dividing our units, same units, dividing the same units, we say we are canceling. They're canceling out. We say canceling out the units. In other words, we end up with no units. Okay? So we can multiply and divide numbers, and we can multiply and divide words, can't we? All right, so that's how we're going to do conversion factors. Now, where did we say conversion factors come from? They come from where? A relationship. What about the relationship? What are we supposed to? A true relationship, and we divide out the ratio? Okay. That's how we get conversion factors. From true and valid relationships, and you divide them out. And then once we get the conversion factor, we multiply with it. And that is dimensional analysis. But the cool thing about dimensional analysis is that it helps us get the right conversions going. So let's just practice that. Let's take days and weeks. All right, let's say we have, 14 days. 14 days. And I want to know, hey, how many weeks is that? All right, now you think, how many weeks is that? Now, I have 1 unit and I want to change to another unit, so I'm supposed to use what? A conversion factor? Okay, this conversion factor needs to relate these two units. And it is going to be 7 days in a week. And then I'm going to change that to a conversion factor, right? Okay, so that's what you do. You have 2 units. You come up with a conversion factor. But the problem is I have 2 conversion factors. Oh, which one do I use? Ooh, I want to change days to weeks. That means I have to cancel out the days. And remember, the only way we said we're going to cancel out the words is if we do what with it? Divide. So I got to use the one that divides by days. Yeah, it's this one. All right, so let's put that in here. So I'm going to multiply, and I'm going to say 1 week divided by 7 days. Okay, now these are multiplied by the fraction because I'm dividing by days, so these cancel, and I'm left with weeks, so my answer becomes 2 weeks. Well, what if I use the other conversion factor? This is where you always watch the units. If I said 7 days divided by 1 week, wow, let's multiply this out. I got days times days. What does that give me? Days squared divided by a week? Okay, well that does not make any sense, does it? So this has a built-in method to make sure you're going in the right direction with your conversions. Okay, so the units must cancel. So we multiply them together and the units must cancel. So how do we do this? We identify the given unit for the days, come up with the conversion factor where the units are canceling. That's all there is to it. So let's see. You guys could do this one. Let's try one where we're going from inches to centimeters. Okay, so we have our 2 conversion factors. So let's see if you can do this one really quick here. Convert 8.5 inches into centimeters. Okay, see if you can figure that out. Set it up. Okay, so you got the 8.5 inches, and you want to change that to centimeters, so you know what unit has to cancel out, right? Which one do you want to get rid of? You want to get rid of the inches. So you know which one units you're going to use, aren't you? Okay, so you know which conversion factor we're going to use. We got 2 conversion factors up there on the board. Which one is the right one to use? Oh, awesome. Like those PowerPoints. I know, that's fun. How are we guys doing back here? Good? Okay, so it looks like we got it. Now turn to your neighbor and double check your answers. And talk about it.
Yeah, because you're using 2.4 centimeters over. Cancel out.
Did you get the right answer? Well, and we watched our sig figs, didn't we? Whenever we do calculations, are we always going to be thinking sig figs? Yes. Every single calculation you do, you're going to count and pay attention to sig figs. On every homework problem, on every class problem, on every test problem, every single one. Now, there might be a couple answers on that exam that are the same, but they differ in the number of sig figs. You're going to know which one to choose, right? Yeah, you got to pay attention to those sig figs. Watch that dimensional analysis.
Okay, so whenever we write it like this, should we count the sig figs here also? Or
Nope.
is it just, no, just
No,
these?
because this is an exact number. It's 1. It has an infinite number of sig figs and decimals. All right, so what did you guys get for your answer? 21.6? 21.6 what? Centimeters. Okay, so the unit that you used was what units? I mean, what conversion factor? 2.54 centimeters on top and 1 inch on the bottom, so that these inches can cancel, right? Okay, we can write it like that, but I'm going to show you another way that I like to write this, especially when we get going with lots of them. It's a little bit easier. I start with my unit, 8.5 inches my started, and then I draw a line, and then I do these hash marks. Okay, and if I had more conversions, I'd do more hash marks. And what I'm going to do is I'm going to write in 2.54 centimeters on top and the 1 inch on the bottom. Okay, so I'm drawing the lines like this. If it's side by side, that's multiply. If it's top and bottom, it's divided. Okay, so I'm going to do it this way just because it's faster than writing that time symbol in parentheses and all of that. Now, you got to remember to keep the units. Now, the sig figs was 21.6. Oh, let's count sig figs. We're multiplying and dividing. Answer must be least number of sig figs. How many sig figs? 8.5. 3, because we have decimal, right? 3. How many here? 3. How many here? That's an exact number, isn't it? It's always 1 inch. It can't be 1.8 inches, right? It's 1.0000000. Remember we talked about it has an infinite number of sig figs? So this is an exact counted number, and it has an infinite number of sig figs. So the least number would be 3, infinite. What's the least number? 3. That's why my answer has 3 sig figs. Okay? So when you're doing this, you're not going to pick 1 sig fig, are you? No, because that has an infinite number. So 3 is the least amount. So it's 3. All right, does that make sense? Okay, super. Let's do some more. Woo, we're having such fun with this one. All right, well, we just did 1 conversion. Oh, that was so easy. My gosh, just 1. Let's add to that. Let's do 4,338 milligrams, and I'm going to change that to kilograms. Okay, thinking about that table that I memorized, there's no conversion between milligrams and kilograms on that table. The only thing I remember is what? Milligrams to what? Grams, and then grams to kilograms. Didn't we have that on the table? Okay, so when you're doing something like this, and you're like, I don't know that conversion factor, then you might need multiple conversion factors, and you can always take it to the base unit, which in this case is grams. So I'm going to do that. So I'm going to go from milligrams, and I'm going to change that to grams, and then change that to kilograms. So in this case, we're doing more than 1 conversion factor. And when we do that, we write what's called a road map. A road map helps us understand what the units are that we're going to change from one to the other. And every time I have this symbol, this means I need a conversion factor. Okay, so for every symbol, I need a conversion factor like this. So what I'm saying is milligrams, conversion factor, to change it to grams, another conversion factor to change it from grams to kilograms. Okay, so let's set this one up. All right, I've got milligrams, and I want to change it to grams. So think about that valid relationship. Okay, so you guys remember that relationship? 1 gram is 1,000 milligrams. Okay, that's the relationship. Now, what unit, let's do units first. What has to go on the bottom? Milligrams. So do you see why we're going to put the 1,000 milligrams on the bottom? It has to. Why does the 1,000 milligrams have to go on the bottom? That way they cancel. And then the 1 gram goes on top. Okay, now that one's done. Let's go again. What do I have on top? Grams. And what am I trying to get to again? Okay. Oh, wow. What was that relationship? 1,000 grams, 1 kilogram. Okay, so I've got grams on top. What do you think I have to put on the bottom? 1,000 grams. It has to be grams, doesn't it? And then what goes on top? Kilogram. Okay, so the units cancel. Whatever's left, that's what your answer comes out to be in. So now let's count sig figs. How many sig figs do I have here? 4. How many sig figs here? Infinite, infinite. How many here? Infinite, infinite. Isn't this an exact counted number? Don't we define 1,000 milligrams are in a gram? We didn't say 1,000.2, did we? No, it's exactly 1,000. No more, no less. We didn't say 999.9. No, it's 1,000 is exactly, it's an exact number. 1,000 milligrams in a gram. Do you see how that's an exact counted number? All right. So how many sig figs does this one have? Infinite. 1 kilogram is infinite. And 1,000 grams? Infinite. Perfect. So I've got 4. Infinite, 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 infinite. How many should I have? 4. So I'd have 4. And we can put this in scientific notation because it's a bigger number. Or I should say more decimals. 10 to the minus 3 kilograms. All right, that's a roadmap. And that's how we do multiple conversions. Well, let's practice doing road maps a little bit more so we can get some ideas of the concept here. All right, let's say I want to go from century to seconds. Let's go from a century to seconds. All right, so we don't have a conversion factor between century and seconds, do we? No. So are we going to have to step it through some units? All right, so let's talk about what those units are going to be. All right, so I'm starting off with century. If you were to do your roadmap, what would you say? Century convert to what? Years. Okay, do you know that unit? Yeah. Okay. And then you're at years. Now what are you going to go to? Day. We're not doing leap year. Okay. Years and months, we could do that. Okay, but now what? Days and months are not quite very, that's not a, 30, some months are 30, 31. Maybe I don't want to do months. Maybe I want to go weeks instead. Okay, so let's do weeks. There's 52 weeks in a year. And then what? Days. And then what? Hours. Then what? Minutes. Then what? Seconds. Perfect. Okay, that's one. What's another one? Could we do another one? What if I don't know the conversion factor between a century and a year? Maybe I only know century and a decade. I could do that. Sure, I could do that. And then I could go decades to what? Years? Okay. And then I could go to weeks. Or if we don't take into account leap year, maybe I could go from years right to days, couldn't I? And then we could do the same thing. Days, hours, minutes, seconds. Okay. You see how that works? All right. Well, maybe I might do this. I might say century, and then I might go to decade, and then I might go to years, then I might go back to decade, then I might go back to years, and then maybe days, and then again hours, minutes, seconds. Well, maybe this one, I know how many seconds there are in an hour, so maybe I don't need to do that. Maybe I could go directly from hours to seconds because I know that conversion factor. I could do that. So are any one of these particularly wrong? No. Could I use any one of these? Yes. That's the thing about these conversions. There's not always an exact one way to do it. Some of you might know more conversion factors than another. Your roadmap may look slightly different from someone else's. But the key point is that you must have true and valid relationships with each conversion. Each conversion has to have a true and valid relationship. Can't be making up stuff. Okay, and if so, and your units cancel, then you can use any one of them. Now, some of them are directly and shorter. It's like a road map. You're going from here to Dallas. Can we take different roads to get there?
Yeah.
Sure. Some of us might go directly there. Others might take the scenic route. And some of us, decades to years, back to decades, back to years, some of us might want to drive around the block a few times. That's okay. All right, as long as we get there and the units are correct. Okay, so that's the idea of road maps. So when you do these big long conversions, write your road map out so you can get an idea of where you're going, and it'll help you as you step it through. Now, what conversion factors are we going to need for dimensional analysis? Don't be Googling up different conversion factors. Okay, don't Google those things because you're not going to be able to Google conversion factors on the exam. So, what conversion factors, can I borrow your book? What conversion factors are we going to need? All the conversion factors that you need for this course, exam, homework, and everything else, is going to be in the back of your textbook where it says useful conversion factors and relationships. Okay? This is going to be provided to you on the exam. This is all you need. So when you're working your homework problems and you're working on things and you're practicing, come to here and use these ones. Don't Google up other ones. Don't Google other ones. Just use these for those are your conversion factors. Okay, so that's the only ones you're going to need, those conversion factors. Thank you. Okay, so that's road maps. So we can do simple conversions. We can do lengthy conversions. Let's do it. That was so easy, right? Was this all easy? Okay, let's do something a little bit more complex. We're going to do this one, and we're going to do one with squares and cubes. All right, we got this. This is so easy. Let's convert 3.73 times 10 to the 8 cubic kilometers. So if it's cubed, it means volume, right? We're going to convert that to liters. Let's do our road map. How would we do that? Cubic kilometers, and you have liters. Well, how are you going to convert cubic something to liters? You guys remember? Okay, so we know that cubic decimeters is a liter. Okay, so I got cubic decimeters here. We also could do cubic centimeters as a milliliter, couldn't we? And then couldn't I go milliliters to liters? Sure. Well, we'll go ahead and go with cubic decimeters. All right, cubic decimeters I can convert to liters. Now, how about kilometers to decimeters? How can I do that? Meters, I can go through meters, couldn't I? Okay, I can go through meters. Now, they have to be cubed, though. Now, here's where the problem is. I don't know the relationship between cubic kilometers and cubic meters. But I do know the relationship is 1,000. I know the relationship kilometers and meters, right? 1 kilometer is 1,000 meters. I know that. But how would I get the cubed one? Well, I can cube both sides. Because is this an equal sign? It's an equation, right? If I do something to one side, I can do it to the other. So if I cube this and I cube this, then cube, remember, means not times 3. Okay, it just means 1 kilometer times 1 kilometer times 1 kilometer. Multiply the numbers, you get 1. Multiply the letters, you get cubic is equal to 1,000 meters times 1,000 meters times 1,000 meters. So what does that equal? 1 times 10 to the what? 9. 9. 1 times 10 to the 9 meters what? Cubed. This is your true and valid relationship. This is what you're going to use to get that conversion factor. Okay? Does that make sense? All right, now we got to do the other one. Meters and decimeters. How are we going to do that one? Well, do you know meters and decimeters? What is it? 1 meter, 10 decimeters, decade, kind of thing, 10 decimeters. Can you get the cubed one? Yeah, how would you do that? Cube both sides. Now if you have this true relationship, now can I set up my units so that they cancel? I can, can't I? You know which one goes on the bottom, don't you? Yeah. Okay. I want you to derive the relationship you're going to use for cubic meters and cubic decimeters, and then I want you to set up this conversion. All right, see if you can do it. And if you're not sure where to go or how to start, check with your neighbor. Make sure your units cancel. You have to cancel those units so you know which one goes on the bottom. And you have to have a true and valid relationship. So we got one of them. You have to get the other. Does everybody know the conversion unit between cubic decimeters and liters? What is it? 1 cubic decimeter is 1 liter. Okay, does everybody know that relationship? Okay, so get that one. You guys getting it? Okay, you know what units have to go on the bottom. You've got cubic kilometers on top. Guess what goes on the bottom? Cubic kilometers. And you've got this true and valid relationship. So you put that one in. Okay, so watch the road map. Watch your road map. You're going from cubic kilometers to cubic meters. You got that. And then from cubic meters to what? No. Cubic meters to what? Cubic decimeters. And then you got to go again from cubic decimeters to liters. Okay? All right. Did you put cubic kilometers on top? Did you put cubic kilometers on the bottom? Okay, what's that true and valid relationship? What did we say? 1 cubic kilometer is 1 times 10 to the 9th cubic meters. You get that? That was we got that conversion factor. Okay, good. Now you got to get the next conversion factor. Okay. So remember our conversion factors. Okay, we got that conversion factor. Now you need the next one, because you're going to have cubic kilometers on the bottom, cubic meters on the top. So I need another conversion factor with cubic meters. How am I going to get that? 1 meter is 10 decimeters.
Final answer. It's going to be this power. We do not. We have to multiply them, right? It's like all. Yeah. Okay.
Is that right?
Thank you.
And
Perfect.
is that right?
Yes, yay, you still got it. Awesome. Okay, keep going. Okay, so you see how, did you know how we get from here to there, right? We cubed it. So how are you going to go to here to a cube?
1,000 meters equals 1 kilogram.
Yeah, but no, because 1 meter is 10 decimeters. But we want to cube it. Just like we said, 1 kilometer is 1,000 meters, and we cubed it. So 1 meter is 10 decimeters, and now we cube it. So do you see how we did this one? And then we cubed it? Because we had 1 kilometer equals 1,000 meters. That's what we started with. And then we cubed it. And then this is how it looks. So now you have the same thing. So you have 1 meter equals 10 decimeters. Well, that's like what we did here. And we cubed it. So now we're going to cube it.
Okay.
And then you know how to write out the cubes, right? So write out the cubes.
Okay.
Except that doesn't go there. It's a cube. It's just meters times meters times meters. That gives you meters cubed.
Okay.
Okay, now cube it out. And then that's going to be your next conversion factor.
Okay.
Good. Excuse me.
Sorry.
It's okay. How are we doing back here? Good? Making sense? Are we cubing it? Getting that other conversion factor?
Cubic meters,
Okay.
cubic decimeters. So you're just gonna have to cube that.
How are we doing back here? Are we getting it or are we lost? Completely lost.
I just want to know which one is greater unit, centimeter or decimeter? Decimeter, right?
1 meter has 10 decimeters.
And 1 meter has
100 centimeters.
And decimeter is bigger.
Decimeter is bigger than a centimeter. Yes.
You know, she's saying that centimeter is bigger and
Well, we're thinking bigger as in more of them. There's 100 of them in a meter. I guess it depends on how you want to look at bigger. Okay, so you got that right, and then you got to put cubic meters to cubic decimeters. Perfect. That's perfect.
Like, what do I do next? How do
Well, then you go to you got this one. So this is what the roadmap is for. So it tells us what to do next. You did this, you did this. Now we got to do this. So that's what you do next, is you do this one next. So that's why we use a roadmap to kind of tell us, because sometimes we're so working on the conversion rate, like, where was I going again? And this is what that's for.
Okay.
And then you have to think of a true and valid relationship between those two. Okay, good. All right, so keep going. What have you got? This word right here is what? Cubic meters. So guess what word you're going to put right down here? Yeah? No, what's this word? Meters and decimeters, do they cancel out? No, that's the wrong one. So this isn't going to work.
So I have to put
What is that word? Cubic meters? Unit is cubic meters?
meter cube. Yeah.
So what are you going to put on the bottom? Meters cubed.
Cube.
Oh, well, here's meters cubed.
Yeah. So I
So you have to put meters cubed. You have to put meters cubed.
What did you do about 3 meter cube?
No. 1 times 10 to the 3 is cubic decimeters. You don't want cubic decimeters. Didn't we want cubic meters? So which one is the cubic meters? This is the cubic meters. So it's 1 cubic meter. It's 1 goes with the cubic meter. 1 times 10 to the 3 goes with the cubic decimeters. So we can't just like change it up, mix and match it. This is 1 cubic meter. So 1 cubic meter has to go on the bottom. So write 1 cubic meter. You see why we have to do that? It's because your units have to cancel. If you put cubic decimeters, they're not going to cancel. It's not going to work. So then what goes on top? This. 1 times 10 to the 3rd cubic decimeters. Cube, don't forget to put the cube there. Okay, then go again. Because you're almost there. Now you got to do the liters. You got to go from cubic decimeters to liters. So if I have the word cubic decimeters on top, guess what has to go on the bottom?
Meter? Oh, meter cube?
No. What's this word?
Oh,
What is this?
decimeter cube?
So what goes on the bottom?
Decimeter cube?
Yes. You see that? Okay. You didn't cube it. Has to be cubed. 1 meter cubed. So we had to write that conversion factor. So we say 1 meter is 10 decimeters. Then 1 meter cubed is 10 decimeters cubed. Right? So 1 cubic meter is equal to 10 times 10 times 10 cubic decimeters. Not that. See, you see how this is meters cubed? So you better have meters cubed. Well, 1 meter cubed does not equal 10 decimeters. 1 meter cubed equals what? 1,000. 1,000 cubic decimeters. Not 10, 1,000 cubic decimeters. You see how you have to have the true relationship? And the units have to match. That has to be cubed.
Cubed?
Yes. You see how these have to match. You don't have a choice.
Okay.
All right, so there's this word, cubic decimeter. So guess what has to be there? Cubic decimeters. Now you know what the relationship is, right? Remember that? We talked about 1 liter is 1 cubic decimeter, yeah? Uh-huh. Okay, does that make sense? Good. Awesome. Exactly. It just takes practice. Perfect. All right, so did we get the answer? Did you guys find the relationship between cubic meters and cubic decimeters, right? Yeah? Okay. You guys got that? Is this looking right? Okay, you know your units are canceling, right? So what do we get? What unit is that? Liters. Okay, did we come up with that? Everybody got it? That's how it looks? Make sense? Okay. You are watching it in your calculator, are you? Are you using that EE and the EXP button? Yeah, be very careful about that. Also, in your calculator, if you want to, if you're going to type this in, sometimes we have calculator issues, you can say this times this times this times this and write a number down. Then you say this times this times this and you write a number down at the bottom and then you divide the two. You can do that, fine. Or, you can put this top part in parentheses, and you can say this times this times this times this in parentheses, divided by, you have to put another parentheses to say this times this times this. Okay? Don't forget the parentheses. Okay, that's one way. Let me tell you another way. If you don't want to do, the parentheses thing, dividing the whole top and then parentheses and bottom parentheses, I like to do it this way. I like to say this number times this number divided by that number times this number divided by that number times this number divided by that number, and just work my way down. And I don't have to do parentheses or write down what those numbers are. So that's an idea. Okay. Questions? All right. Okay, how are we doing? Good? Okay, do you guys have questions, or are we good? We good? Yeah. All right, let's go on to the next one. Okay, this time, notice, you know when we did these, we never had anything under here? Okay, well now we're going to put something under there. All right, so now we can do cubes. It's like, hey, let's add something else. Yay! All right. Let's talk about this one. Gosh, gas prices are falling like crazy, aren't they? Yeah. Gas prices went like crazy, rising. Remember, just up and down. Okay, well, the cost of gas has risen everywhere. In Japan, the cost of gas was 161 yen per liter in the summer of 2008. How much is that in dollars per gallon if the exchange rate was 108 yen per dollar? What's my starting unit that I'm working with? Yen per liter. And what am I trying to change that to? Dollars per gallon. Okay, so here we go. I've got 108 yen. Now, how am I going to write that? Yen per liter. Okay. It would be per liter, so I'm going to put 1 liter. That's per liter. So now we have something on the bottom. 1 liter. Okay, now what I want to do is convert that to dollars per... Oh, I'm sorry. 161. Ooh, good catch. 161 yen per liter. Okay. And then I'm going to change that. I'm going to convert that to dollars per gallon. So what we're doing is essentially two conversions. Yen to dollars and liters to gallon. So what it is two roadmaps. So I've got yen going to dollars, and then I've got liters going to gallons. All right, well, let's take yen to dollars. Do I have a true and valid relationship that gets me between yen and dollars? Yeah, what is it? Yeah, that's the 108 yen per dollar. Okay, that's my conversion factor here. 108 yen equals $1. Okay, well, what about the next one? Liters to gallon. We're like, how do we do that? Well, and you look in the back of your textbook and you find the conversion factor. That's true. We could say 1 gallon is 3.74. Let's just say we don't want to use that one. Let's just say we want to use the quarts one. Wouldn't that be more fun? Is there a quarts one? Liters to quarts?
1 liter is 1.0567.
Okay, let's do that one. But then do we know quarts to gallons? Does anybody know quarts to gallons? You guys know? Does everybody know that? 4 quarts is a gallon? You're like, no. Okay, that's kind of stuff will be given to you on the exam, but I just kind of want to use that just to throw in a little bit of English. All right, so how do we do that? English metric units there. All right, how do we do that? I've got yen on top. What goes on the bottom? So I'm gonna look at my conversion factor and I say, oh yeah, it's 108.0, and what is it on top? $1. Okay, yens cancel. I'm left with dollars. I'm getting there. Now I got to convert liters, so I can do it all in one chain. So if I've got liters, I need to cancel out the liters. So where am I going to put liters? We've always put it on the bottom. Why can't I put it on the bottom? They won't cancel. It'll be what? Liters times liters, and now we get liters squared? Okay, that's not going to work. So it has to go on top. So I can put liters on top, and then we're going to do quarts. So that's 1 liter is to 1.057 quarts. And then my liters cancel. And then I've got quarts on the bottom, so now what? Quarts on top. Why am I putting quarts on top? Don't these have to cancel? Yes. And then what do I want? I want gallons, right? So it's 1 gallon is 4 quarts. So the answer comes out to be $5.64 per gallon. And that's your answer. All right. Does that make sense? Okay. Whew. Well, that finishes up chapter 1. Oh boy, yay! Woo, all that dimensional analysis and sig figs, and we're going to be using that all the time. So I'm glad it's right there because we're going to be using it all the time. So these kinds of things we're going to be using every time. So when we get and we start doing other problems, we're going to use this stuff to solve those problems. So you got to really nail this stuff down. Okay, well, we're getting ready to start chapter 2. And this will be a good time for us to take a break. So we will come back in 15 minutes and we'll do chapter 2. All right, so let's take a quick break.